Hi, Assalamualaikum all. So for this video, I'm going to explain on the Fourier Transform, the introduction of Fourier Transform, which is part 1 from this chapter. Okay, so these are the outlines of this video. I'm going to show you on the introduction of Fourier Transform and also definition of Fourier Transform. Okay, basically Fourier Transform is one of the methods to transform the signal from time domain to frequency domain. Okay, because for the signal, we have the signals in time domain. So in order for us to process or analyze the signal, basically it's easier to do it in frequency domain. So this is what Fourier transform is used for. Fourier transform can convert a non-periodic signal into its complex Fourier components to produce signal's frequency spectrum. And why do we need Fourier transform? Like I said before, it is easier to study and manipulate the signal in frequency form when compared to in time domain. And there are many applications in electrical engineering, such as filter design to reduce noise, signal processing to restore, enhance image, and signal modulation to transmit low frequency through high frequency carrier wave that basically use the signals in frequency domain. So this is what the Fourier transform is used for. Okay, here are some examples for the waveform which is transformed to the frequency spectrum using Fourier transform. Okay, let's see for the first signal here. This is a harmonic signal. Okay, when it is transformed to frequency domain using Fourier transform, the spectrum will be like this. Okay, and then this is another signal. Okay, and if the duration of the signal is increased and when it transforms to the frequency domain, the line here in the spectrum becomes closer. Okay, so as the duration here increase, it becomes closer and closer. Okay, for the third picture here. Okay, and finally, when the duration of these signals approach infinity, for example, the single pulse, the frequency domain or the frequency spectrum for this time domain signal will become so close together and it will form a line like this. Okay, so basically for the harmonic signals, the Fourier transform will be something like this, and as the duration approaches infinity, the frequency spectrum, okay, or the frequency domain of this signal will become like this. Okay, so why did I show you the previous figures? Okay, this is because that is what define Fourier transform. We already learned about Fourier series. Okay, Fourier series is used to get the frequency spectrum of periodic signal, just like the first figure that in the previous slide. However, when the period of signal increase, the lines of spectrum lines will be closer together. Okay, and if the period approaches infinity, the signal will become non-periodic and the lines will combine to make a continuous curve. Okay, just like the last figure we saw just now. So Fourier transform is basically an application of Fourier series when the period of the signal is approaching infinity. Okay, so in other words, remember the figure just now. Okay, so as the t here approaches infinity, okay, and the Fourier transform will become something like this. Okay, so this is basically an application of Fourier series when the period of the signal is approaching infinity. So mathematically, this is the definition of Fourier transform. Let's say we have a time domain signal. So time domain signal is Vt. So this is the way how we write the Fourier transform. We put f here and this square bracket, and we put the time domain signals inside this square bracket. So it's equal to the integration of this time domain signal from negative infinity to infinity multiplied by exponent negative j omega t dt. Okay, so by performing this integration, we will get the Fourier transform of Vt, which we put as V, capital V, and omega. So remember, when you put the signal in terms of time domain, you write in terms of small letter, which is Vt. And when you transform it using the Fourier transform, Okay, it will become V, capital V, and omega, because this is in frequency domain, hence this omega. And then to perform the inverse Fourier transform, this V omega, we put in the square bracket like this, and the symbol here is f negative 1, which is the inverse Fourier transform, which is equal to 1 divided by 2 pi, the integration from negative infinity to infinity, V omega, okay, which is the one that we have converted to frequency domain, multiplied by exponent j omega t d omega. Okay, so the integration is in the frequency domain, which is d omega, and there is no negative here as opposed to there's a negative here. Okay, so once we do that, we will get back the time domain signal, okay, which is the original signal before it has been transformed into a frequency domain, right? And let's see one example here. The Fourier transform for impulse function. Given a signal which is unit impulse function, Vt equal to delta t. So this is the delta t function. Okay. In order to perform the Fourier transform, we write it like this: f delta t equal to the integration from negative infinity to infinity delta t multiplied by exponent negative j omega t dt. So basically, when we use the delta properties, we will get the integration here equal to 1. Okay, and when we put the pair or the answer of Fourier transform for this delta t, we put it like this: delta t, okay, and the pair of Fourier transform is 1. Okay, so we put f here. Okay, the symbol here shows that if we perform the inverse Fourier transform of 1, we will also get delta t. Okay, so this is the spectrum for delta t, which we put in terms of v omega, because just now we put the signal in terms of vt, okay, small vt, and now we put in terms of capital V, and the domain here is omega, which is the frequency. Okay, recall back the Fourier series for rectangular signal. For the periodic waveform of this rectangular signal, the frequency spectrum will be this line here, okay, this line here, okay, which is in terms of the impulse function. And so as the duration of the signal approaches infinity, it will become something like single signal here, which is a pulse signal here. So if you want to find the Fourier transform of the rectangular signal here, basically using the same knowledge that we understand before, the line of the spectrum will become closer and closer together, and it will form this sinc function. Okay, so this sinc function is actually the Fourier transform of this rectangular signal. Okay, so recall back here for the periodic waveform. If we perform the Fourier series, we will get this line here. The spectrum here is in terms of this pulse function here. Okay, so as the duration approaches infinity, it will become this sinc function, which is the envelope of the pulse function in the periodic rectangular signal for using Fourier series. Right, so to prove the Fourier transform for this rectangular signal, we perform the integration. Okay, for Vt from negative infinity to infinity, and this Vt is multiplied by exponent j omega t dt. So the duration here is between negative tau over 2 to tau over 2. So we integrate the exponent function and a, take out the a, so integrate the exponent function, it will become exponent negative j omega t divided by negative j omega. And we replace this t with tau over 2 and negative tau over 2, and we solve like this. Okay, solve and rearrange so that we rearrange the equation here so that we can put it in terms of sinc. Okay, so for sinc omega tau over 2 is actually a sine function of omega tau over 2 divided by omega tau over 2. Okay, so remember that like sinc t is actually sine t divided by t. So we rearrange so that we can put it in terms of sinc. So the Fourier transform for the rectangular signal is a tau sinc omega tau over 2. Okay, so how do we get this sine function in the first place? Because this, when we obtain this, so using Euler's theorem, okay, we convert it into sine function. Once we obtain the Fourier transform for Vt, which is in terms of the sinc function, and the peak here is a tau, we can plot the magnitude of this sinc function. The magnitude here is on the positive side only, and the peak here is a tau, and this is the phase for this Fourier transform for the rectangular signal. Okay, now we look at another example, Fourier transform for exponent function. Okay, so we want to find the Fourier transform for a exponent negative a t u t. So if this is not correct on your notes, please correct it. And this a exponent negative a t u t, when multiplied by ut function, which is unit step function, it means that this function has only the positive side. Okay, because the negative sides of unit step function is 0. Okay, so anything multiplied by 0 is 0. And we integrate for the positive side only, which is from 0 to infinity, exponent a exponent negative at multiplied by exponent negative j omega t dt, and take out the a, and then solve this exponent and solve the integration here. Okay, put the value of infinity and also 0 at t here. We will get v omega, which is the Fourier transform for this whole function inside the square bracket here, equivalent to a divided by small a plus j omega. You can get or obtain the Fourier transform of this function also by referring to table C2b. Okay, so in the table, which is in the list of formulas given to you during the test, also final exam, you will see that the pairs for the exponent function multiplied by ut is here, a divided by a plus j omega. So hence, to get the magnitude and phase spectrum, to get the magnitude, you use this formula or this way to get the magnitude. And for the phase, and on how do you want to plot the phase, you calculate the arc tangent of omega divided by a, and the phase should be the negative of this arc tangent. Okay, this is how you want to transform, or how do you want to plot for the Fourier transform in terms of frequency domain, and also in terms of the phase of that frequency domain. Okay, okay, why do I say just refer to the table? Okay, basically, for our syllabus, normally you will be asked to just refer to the table. Okay, you don't have to actually calculate this integration. However, you need to understand how do you obtain from here up until here. Right, so for this subject in a system, normally it is based on the application of the Fourier transform. So you just know on how to use this formula in the table. Okay, and how to get this formula in the table. Okay, this is the amplitude and also phase spectrum for this function in time domain, which is Vt, a exponent negative a t u t, and this is a. Okay, so this is a v omega. Okay, and this is the phase for this v omega. Okay, and finally here we want to find the inverse Fourier transform for impulse function. We just use the term here, the symbol f negative 1, which shows the inverse of Fourier transform, the square bracket, because we want to find the inverse for impulse function, so we put delta omega, okay, which is in the frequency domain. So when you put the inverse Fourier transform, you cannot put in t here, okay, because t here refers to time domain. So because this is inverse of Fourier transform, it means that you want to find from Fourier transform of frequency domain into time domain. So using the formula 1 over 2 pi integrate negative infinity to infinity delta omega multiplied by exponent j omega t without any negative d omega. Okay, so solve for this, you will get 1 over 2 pi. So in order for us to put the pairs, okay, 1 over 2 pi is actually the Fourier transform pair of delta omega, or 1 is actually the pairs for delta omega multiplied by 2 pi. So if we have time domain, in terms of the straight line here, which has the value of 1, which is actually the normally the DC value. So the Fourier transform for this VT is the pulse function, which is 2 pi delta omega. Before I'm going to show you how to solve some examples, I'm going to show you the table of C2A, which is given in the list of formulas. Okay, so there are some of the time domain function with the Fourier transform pairs. For example, just now we already obtained how to get Fourier transform for delta t, which is the impulse function, and this is the time domain function. Okay, the shape of the time domain function, and this is the Fourier transform, the Fourier of Fourier transform, which is 1. Okay, and this is the shifted impulse function. So if the impulse function here is shifted by t naught, the Fourier transform here will become a exponent negative j omega t naught. And this is the Fourier transform for the step function, okay, given like this. And you do not have to perform the integration at all, because you can just use the table. However, when the Fourier transform pairs here is combined with the Fourier transform properties, then you need to know how to apply that Fourier transform properties. Okay, and this is some of other waveforms of the time domain signal here in terms of the signum function, increasing exponential function, cosine function, sine function, and also rectangular function. And these are the pairs of this time domain function in terms of frequency domain. Okay, so there are some more time domain function listed in the list of formulas. Okay. Okay, now we want to find the Fourier transform for G1t, given as 5 exponent negative 1 5t ut. So first of all, we refer back to the Fourier transform pairs listed in the list of formula. So we find out that for the exponent function or decaying exponent function, the pairs for exponent a exponent negative at ut, in which a here is a real number bigger than 0, is a capital A divided by a plus j omega. Okay, so for this example here, capital A here is, okay, what is the capital A here? Okay, this is 5. Okay, and then small a here is given as 1 over 5. Okay, not negative 1 over 5, because in the original form, this is already negative. So we just take a here, mesh with this, which is 1 over 5. So from here, we can get the Fourier transform for G1t written as G1, okay, the capital G, 1 omega equal to, okay, so 5 on top here. So this is equal to 5 divided by 1 over 5 plus j omega. So as simple as that. Okay, so you don't have to solve further. Okay, this is the Fourier transform for G1t. Okay. Right, next we're going to solve the rectangular function. Okay, we are going to find the Fourier transform for G2t equal to 1 over 3 rectangular 3t. So we refer to the list of formulas. This is actually a square function. So for the square function, it is given that the pair for rectangular function a rectangular t over tau here, and the pairs of Fourier transform here is a tau sin omega tau over 2. So from here we need to match with this form. Okay, a here is given as 1 over 3. So a is 1 over 3, and t over tau here is whatever inside the bracket here. Okay, so take out the t here. 1 over tau is 3. Okay, 1 over tau is 3. So tau here is actually equal to 1 over 3. Okay, because 1 over tau is 3, so we arrange tau is 1 over 3. So put all of these values back into this equation and write the proper Fourier transform form for G2. So the capital G2, okay, and the bracket is omega. So remember, don't make this mistake. When you have transformed using Fourier transform for time domain signal, there's no longer t domain. Okay, so you put in terms of omega. So we put a, which is 1 over 3. Okay, and then another one is tau, which is also 1 over 3. Okay, and then put sinc omega and tau again, which is 1 over 3 divided by 2. Okay, so solve for this, you'll get 1 over 9 sinc omega over 6. So this is your answer for the Fourier transform of G to T. Right, another example in the exercise 2, we need to find the Fourier transform for G3T given the function here is tri, which is a triangle function, 5 tri 4 over 3t. So again, refer to the list of formulas. In the list of formula, it is given that a tri t over tau, the Fourier transform pairs here is a tau sinc squared omega tau over 2. So again, you don't have to perform the integration. Okay, you can just refer to the table. So from here, we match this here, okay, a tri t over tau with the original form in the time domain. And we obtain here a equal to 5, okay, and tau here is 3 over 4. So using this a and tau, you put back in this equation. You write the proper frequency domain form for the Fourier transform, which is G3 omega equal to a, which is 5, multiplied by tau, which is 3 over 4. Okay, sinc squared, and then omega over 2 multiplied back by tau, which is 3 over 4. Okay, as simple as that. Just put in the formula and then solve this. This is 15 over 4 sinc squared 3 omega over 8. Okay, so this is the answer for this tri function. Okay, so the next one is G4T and also G5T. So I leave these two equations for you to solve. Just find the Fourier transform for this G4, which is the exponent function. Please try to look at the table, okay, and mesh the signal, the time domain signal is whatever in this equation, okay, in the equation here. And this one is a sine function. Okay, so we move to another exercise, exercise 3. We need to find the inverse Fourier transform for the given function here. So it looks very long, but first you have to find in the list of formula, okay, on the third column for the Fourier transform pairs. Okay, you find whichever has the equation that matches this, okay, that matches this equation. Okay, so when you look at the table, okay, you will find out that the cosine function will have something with this will have the Fourier transform with this form. So the way you write this, you find out that from the table you put here cosine omega naught t ut is the press for the Fourier transform here is pi over 2 delta omega minus omega naught plus delta omega plus omega naught plus j omega divided by omega naught squared minus by omega squared. Okay, we mesh with the original equation in the frequency domain here, right? So we know that there's another number here, which is 5, which is the amplitude of the cosine function, and omega naught here is 5. Okay, so from here we can obtain the inverse Fourier transform of v1 omega, which is v1t, sorry, not vi, v1t, equal to 5 cos 5t ut. Okay, so this is the answer. Okay, And for another example here, V2 omega given by this equation, 30 pi, also we have delta function, delta omega minus 10 plus delta omega plus 10. So this is where you have to be very careful. Okay, you have to really match the Fourier transform with the time domain signal. Okay, the pairs of that Fourier transform with the time domain signal. So for the cosine and sine function, there will be two different kind of signals. Okay, the one that we did before here is cosine function multiplied by ut. So there is another cosine function which gives us the pairs of the Fourier transform domain, which is cos omega naught t. Okay, the pairs for the frequency domain for the transform here is pi delta omega minus omega naught plus delta omega plus omega naught. Okay, so there is another element missing here if you compare with omega cosine multiplied by unit step function, which is this part. Okay, this part is not here. Okay, and this is not divided by 2. So from here we can mesh with this. We know that 30 here is the amplitude. So we will get V2t here is equal to 30 cos 10t. So this is the inverse Fourier transform for V2 omega. Okay, and as in the exercise 4 here, we need to find the inverse Fourier transform for this function V3 omega. Okay, so you mesh and you try to find the closest mesh of the Fourier transform with the time domain signal in the list of table. So from the table, I found out that the Fourier transform pairs for unit step function is given as this step function with the amplitude A, and the Fourier transform here is given by A pi delta omega plus 1 divided by j omega. Okay, which basically match the form here. So we know that A here is 7.5. Okay, so we can put in this, just put in this equation. We will get V3t is equal to 7.5 ut. Okay, as simple as that. Okay. And then now we move to V4, which is given as 3 divided by 25 plus 10 j omega minus omega squared. Okay, from the table, I found out there is one time domain function which is t exponent negative at ut, which has the Fourier transform pairs given as 1 over a plus j omega squared. So if we solve for this, we will get 1 divided by a squared plus 2aj omega minus a omega squared. Okay, which actually match this form. Okay, putting into the equation, we will get v for t, okay, this is a small v, equal to 3t exponent negative 5t ut. Okay, because a here is actually 5. Okay, because a 5 squared is 25. So this is the answer. Okay, so that's all for this video, for the first video lesson for Fourier transform. So we meet again in the next video lesson. Thank you.